The purpose of this experiment was to understand how a fluid moves around a cylinder using visual and quantitative data. The data was collected using pressure ports over the cylinder alongside a video camera, smoke, and laser setup to visually see the flowing air. One of the primary objectives of this lab was to understand how to manipulate a boundary layer across a surface using different wind tunnel speeds and different surface roughnesses. As the flow separates from the cylinder, it will often create an oscillating flow known as vortex shedding. This effect is best seen in the video of the flow because as the tunnel speed increases, it is clear to see that the vortex shedding effect decreases. In a similar manner, by adding surface roughness to the cylinder via trip strips, the flow stayed connected longer. Alongside this, analysis of the pressure port data supports these conclusions and gives more insight into how the flow behaves along different areas of the cylinder. In conclusion, flow will stay most connected to a cylinder at higher wind speeds and by energizing the flow via surface roughness. Further tests may be conducted to find the best materials and areas on the cylinder to place these trip strips to most reduce vortex shedding. In fluid dynamics, vortex shedding is an effect that occurs when flow becomes turbulent and oscillates behind an object. Flow on both sides of the object periodically detach at different rates, creating a snapping effect that is easily seen in videos of flow over a cylinder. Similar to other types of turbulence in airflow, this flow pattern will take energy out of the fluid and create substantial amounts of drag. This shedding also has the potential to match the natural frequency of an object such that the object can become damaged or dislodged. This effect can negatively impact any type of cylindrical object, including power lines, smokestacks, and most famously, the Tacoma Narrows Bridge in Washington. By carefully observing this effect and the conditions that cause it, we can design situations that either avoid or demonstrate vortex shedding. After performing safety checks, the tunnel was run at various speeds to test and visualize the way the flow was moving around the cylinder. It was run at 150, 300, and 600 RPM. The goal was to test at different speeds and Reynolds numbers and compare the behavior of the wakes. Pressure data was collected by Kehney valve through 24 pressure ports equally spaced around the cylinder and compared to the static pressure at the inlet of the wind tunnel. Note how the ports were placed in a spiral around the cylinder and offset from each other. This is so any turbulence caused by the change in surface geometry does not interfere with the readings of any other ports. At each speed, a team member on top of the wind tunnel shined a laser down. When a smoke trail was introduced into the stream, it reflected the laser and revealed the characteristics of the flow. With some communication and adjustments, the different behavior of the air around the cylinder could be seen at various speeds. After that, rough strips were put along the cylinder as seen here to attempt to trip the flow. All tests were then repeated and compared to the non-tripped flow. The data was finally analyzed in MATLAB after the fact, and the coefficients of pressure and drag, the force on the cylinder, were determined and plotted. By analyzing the videos and watching the speed at which vortices were shed, the Strohal number could also be determined. The theoretical coefficient of pressure plot is derived using the assumptions of a steady and inviscid flow over the cylinder. At the leading edge of the cylinder, corresponding to port 13 in our data, the oncoming flow is brought to rest, leading to a stagnation point. The inviscid theory predicts that the flow from this stagnation point over the top and bottom of the cylinder would remain attached all the way to the trailing edge. The symmetry of this theoretical relationship, Cp equals 1 minus 4 sine squared theta, is unrealistic because it implies that there is no drag on the cylinder. However, in the plots of coefficient of pressure, coefficient of drag, and the videos of flow over the cylinder, it can be seen that the flow does not stay connected on the cylinder the whole way around. The assumption of smooth flow at the trailing edge to meet the Kutta condition is not accurate because of the viscous flow. Unlike the ideal scenario, the viscosity of the flow will result in a thin boundary layer adjacent to the cylinder. The flow separation occurs because the flow at the boundary layer is losing energy due to the viscous friction between the boundary layer of the air and the cylinder's surface. A trailing wake forms on the downstream face of the cylinder. Along the forward face of the cylinder, the pressure should be highest at the stagnation point and should drop as the flow accelerates to twice the free stream velocity at the top and bottom, and then it would decelerate, causing an increase in pressure as it traveled to the back of the cylinder. However, as the flow reaches the top of the cylinder, the pressure remains relatively low due to the vortices caused by the flow separating. It can be seen in the plot of CP and CD that the flow becomes disconnected at around 45 degrees from the stagnation point at both 11 and 26 meters per second. This separation occurs because the pressure is increasing in the flow direction, creating an adverse pressure gradient. The fluid particles fail to move against the increasing pressure, and boundary layer separation occurs. It is clear that the flow has become disconnected past this point because the standard deviation of the coefficient of pressure is very high. This implies that there is a large variation in pressure, which is commonly caused by vortices that form as the free shear layer due to the boundary layer separation roll into a discrete vortex and are shed from the surface. When the flow over the cylinder is tripped, the boundary layer is energized, giving it more energy to remain attached to the surface. The locations of the sandpaper strips, installed 75 degrees above and below the stagnation point, were determined based on observing where the flow separated. This is clear in the plots of both CP and CD. It can be seen in the coefficient of pressure plot that the flow becomes disconnected around 75 degrees above and below the stagnation point, which is roughly 30 degrees past that at which the flow became unattached when the boundary layer was not tripped. The flow remained attached past the top and bottom of the cylinder and the wake became warm and Aero. The coefficient of pressure continued to decrease from the stagnation point until 75 degrees around the cylinder because the pressure gradient on the downstream surface is smaller. The corresponding pressure drag for a tripped boundary layer is reduced. This effect can also be seen in the plot of coefficient of drag and the drag force at each point. To calculate the drag force, it was assumed to act over the entire 15-degree panel of the cylinder, and each port is taken to be at the center of said panel. The plot of the drag force on the cylinder shows that the drag force on the cylinder is much greater at a higher Reynolds number, corresponding to a wind tunnel speed of 26.5 meters per second, than at the low Reynolds number, which corresponds to a wind tunnel speed of 11 meters per second. The drag plot should appear to be a cosine shape symmetric about the x-axis, which would result in a net sum of 0. However, because the flow becomes unattached at the back of the cylinder, there is a low pressure region in the back, which effectively pulls the cylinder back, and results in a non-zero positive net drag force. When the boundary layer is tripped, the flow stays attached longer and more closely resembles a cosine shape predicted, and results in a non-zero but somewhat smaller drag force than that without the tripped boundary layer. The difference in total drag can be seen in the plot of CD versus the Reynolds number. For the untripped flow at 5 meters per second, we calculated a Strohal number of about 0.07, and for the tripped flow, it was calculated to be about 0.03. The theoretical Strohal number should be around 0.2, so these values do not make much sense. This is because it was very hard to observe the frequency at which the vortices were shedding off the cylinder. These poor conditions were caused by the large amount of light in the room and the lack of smoke because the smoke machine was malfunctioning at the time of testing. Because it was difficult to observe the frequency at which the vortices were shed, an attempt to calculate the Strohal number for speeds greater than 5 meters per second was not taken. Although the Strohal numbers calculated for the flow around the cylinder at 5 meters per second were not accurate, it can be seen that the frequency at which the vortices were shed from the cylinder was reduced when the boundary layer was tripped by the sandpaper strips. From the flow visualization in the two tests, tripped and untripped, it is clear that adding roughness to the surface of the cylinder tripped the boundary layer and allowed the flow to stay attached to the surface of the cylinder longer. This is because adding roughness increases the energy of the boundary layer. The flow being attached for longer resulted in a change in the coefficient of pressure values. These values were more similar to the inviscid graph for CP, since in that assumption, the flow would be attached from the leading edge to the trailing edge. The graphs show that the pressures at the leading and trailing edges of the cylinder for the tripped flow were significantly lower than the non-tripped flow. The flow separation at the back of the cylinder creates a low pressure region in the back, creating a drag force. When tripped, the flow is attached for longer, creating a smaller region of lower pressure. This imparts a smaller drag force and smaller coefficient of drag, which can be seen in the plot of CD versus Reynolds number. This effect is also caused as the Reynolds number increases. When the flow was tripped, the frequency of the vortices also decreased, which resulted in a decrease in the Strohal number. Some of the plots aren't perfectly symmetrical due to the flow not being two-dimensional. The flow is able to travel in all directions, not just over the face of the cylinder. If a sphere was used instead of a cylinder, similar coefficient of pressure and coefficient of drag values would be recorded, and the flow characteristics would act similarly since the curvatures are identical. However, there would be less asymmetry since a ball is symmetric around every axis and the cylinder is not. The Reynolds number for the ball and cylinder would be the same, assuming the diameters of the ball and cylinder are the same. This is due to the Reynolds number being calculated using the length of the diameter and the fluid conditions, which most likely would not change. The coefficient of pressure plots show virtually symmetrical values on the top and bottom of the cylinder for both the tripped and untripped tests, which means that there is neither a lift nor a downward force acting on the cylinder. Cylindrical shapes can be seen in real life on man-made structures, such as light poles and cylindrical-shaped buildings. It is also seen in nature with the cylindrical shapes of trees. Roughness caused by cracks in the trunks of trees and the bark types of different trees can control how the flow separates and thus the drag force on the tree trunk under windy conditions.